So we left off in chapter 15 here, so this is part 2. SN2 reactions of allylic halides and tosylate. So allylic halides and tosylates react quickly by the SN2 mechanism. Transition state of the SN2 mechanism is stabilized through the conjugation with the p orbitals of the pi bond. This transition state has a lower activation energy and explains the enhanced reactivity of these allylic states. So if we look at the mechanism for SN2 reactions, here is a propyl bromide that's not conjugated. The nucleophile comes in, and as the nucleophile is coming in, this will get kicked off. So here's the transition state as this is happening. So you have this formation of the bond while this is leaving at the same time, and then you generate the product. In an SN2 reaction of an allylic bromide, you have that nucleophilic attack, and that's going to get kicked off. Here you have stabilization provided by this pi bond, right, with that p orbital where the nucleophile and bromide is leaving and coming in. And so this stabilization provided by the pi bond allows this to happen better, and then you get the product here. If we look at SN2 reactions with organometallics, allylic halides and tosylates reacts with Grignards and organolithiums, just like a nucleophile, right? So this is as if you had electrons, and so you're going to get the same thing. This will attack that carbon that's interacting or that has a bond with the bromine, and the bromine gets kicked off to generate your product and lithium bromide. In terms of Diels-Alder reaction, this is a new reaction. It's named after Otto Diels and Kurt Alder, who received the Nobel Prize in 1950. The reactions is between a diene and a dienophile, which is an electron-deficient alkene. Produces a cyclohexene ring. Diels-Alder is also called a 4+2 reaction because the ring is formed by the interaction of 4 pi electrons of the alkene and 2 pi electrons with the alkene or alkyne. So if we look at the mechanism, here's your diene and here's your dienophile. The dienophile is electron poor, and this W is showing that there's withdrawing groups on attached to this carbon, making this an electron poor dienophile. And your diene is electron rich. So this is a one-step conservative mechanism. So you can see electrons go over here to form a bond. These electrons move over, and these electrons come to the other carbon of the dienophile, forming the cyclohexene ring, right? There's a double bond right here. Examples of Diels-Alder reactions are shown here. Here are different dienes with dienophiles. Here's a dienophile. This is the electron withdrawing group. Again, the electrons go right here to here and then to here to form the cyclohexene. Again, these electrons, this is an alkyne. Here's your electron withdrawing group on top and on bottom. These go to the back, and then these go to the bottom. This forms this product here. And again, concerted mechanism forming the cyclohexene ring. Again, these are withdrawing groups over here. Diels-Alder product, it's important to note, always contains one more ring than the reactants. 2 ends of the diene forms new bonds to the end of the dienophile. The center, which is formerly a single bond of the diene, becomes a double bond. Dienophile's double bond becomes a single bond, or its triple bond becomes a double bond. In terms of stereochemical requirements, the diene must be in S-cis conformation. Diene C1 and C4 p orbitals must overlap with dienophiles p orbitals to form new single sigma bonds. Both sigma bonds are in the same face of the diene, so there is syn stereochemistry. In terms of overlap of the orbitals of a Diels-Alder reaction, here are your two, this is your diene and your dienophile. As they're coming together, the p orbitals are overlapping, as you can see. So the overlap of the p orbitals of your dienophile and your diene come together in the transition state. And then, as a result, when the reaction occurs, these then become p orbitals, right? New p orbitals. So you have new bonds that are being formed from that p overlap, and a new pi bond being formed. The conformation of the diene is in the S-cis form, even though it's energetically disfavored slightly because of the repulsion. It is what is used in the reaction. Again, this cis bond, S-cis, can rotate to form the trans, which is more stable, and the trans is 12 kilojoules per mole more stable than the S-cis. So if we look at the Diels-Alder rate compared with that of buta 1,3 diene, so we can see here's buta. This is similar to buta 1,3 diene. This is faster, and this is slower. So once you start to see steric repulsion, it becomes slower. And right, if it's in the trans conformation, S-trans conformation, it's less likely to happen. So cyclopentadiene undergoes, which is over here, Diels-Alder reactions readily because of the fixed S-cis conformation, as you can see here. When the diene is sterically hindered, the reaction slows down, even though the conformation can be an S-cis, and then S-trans don't undergo Diels-Alder. In terms of stereochemistry of Diels-Alder reactions, right, you have, I'm not going to show the arrows because I've shown them before. You have the reactions occur where you have electrons move, 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 and you generate the cis product, right, where here the H's are coming out at you, and these esters are going to the back of the board, or back of the plane of this document. Here, if you have an S-trans, when you do the reaction, you have this one going out at you and this one going to the back, so this generates a trans, and you can have the racemic mixture. Here in this case you have the cis-meso mixture, and here in this case, if you have electrons go and move, you're going to get, right, these are in the plane, so there's no stereochemistry here, but over here, because you're reacting, your H's, right, are going in one direction and your CH3s are going in the other direction, and you have the other opposite conformation as well, the other cis version. And then finally, here when you're reacting, see, since the CH3 is on this is pointing up on this carbon, and this one on this carbon, it's also pointing up. The conformations of the methyl groups here and over here will yield this going to the back and this coming to the front, and vice versa, generating trans-racemic products. So stereochemistry is important depending on what the substituents of your diene and dienophile look like. So cycloadditions obey the endo rule, in which the p orbitals of the electron withdrawing groups on the dienophile have secondary overlap with the p orbitals of C2 and C3 carbons of the diene. So here's your dienophile The p orbitals of the electron withdrawing group are shown here, right? So it's shown over here, the CO. There's this secondary overlap that is occurring on the C2, C3 carbon of the diene. And as these are forming new bonds and the new pi bond is being formed, as a result, this substituent goes endo, right? Goes to the back, while these H's go up to the front, right? So these two go to the back. Examples of endo rule. So essentially, in terms of endo is the ones that are pointing down, exo are the ones that are pointing up. So if we look at cyclopentadiene reacting with dienophiles, we see that this group and this bottom group, these will all form, right, in the endo conformation, where the electron withdrawing group will overlap so that it forms the endo product. Unsymmetrical reagents and generates 1,4 products. So if we look at the diene and dienophile, shown with the electron withdrawing groups, it will prefer to form this product. So this would be 1, 2, 3, 4, right? But not the other product where this is flipped down, which would be the 1, 2, 3 product. In terms of predicting the product, the reason why this is only formed is that you can have resonance stabilization, where you have electrons from your oxygen move over, and here electrons move over to the oxygen. As a result, minus reacts with plus, right? So this will go in this direction, right? And then as a result, you generate the 1,4 product over the 1,3 product. If we look at another unsymmetrical reagent, in which now the donating group is on the bottom of the diene, withdrawing group over here, you have cycloaddition, where now you form the 1,2 product, right? 1,2 versus the 1,3, which would be 1, 2, 3. This does not form. Again, you can use resonance to describe this. Electrons are moving over here, so now you have a buildup of negative charge over here, and then the electrons get pushed out, withdrawn, and you have a buildup of positive charge, so you have this interaction where it's going to interact with the positive group, leading to the 1, 2 product over here. So let's do a problem. Look at this proposed Diels-Alder reaction shown above. In this case, you have electron donating interactions from your methyl group come in. I guess over here. This will build up your negative charge over here. And then you'd have electrons being withdrawn over here, building up positive charge. So then your likelihood of interaction would be, actually we can flip this over, where you have now your methyl group and your electrons over here. So when you have this interaction, you're going to have formation of that, so that you generate the product where it's 1, 2, 3, 4. So this is going to be preferred over the 1, 3, right? So I flipped this over just to make it clearer. Here's another example of a Diels-Alder reaction, and we have to predict the product. Again, you're going to look at your electrons. Here, your donating groups, sorry, please bear with me, move your electrons like this, so now your negative charge buildup is down here. In the case of the withdrawing groups, here the electrons are going to move down, this is going to move to here, so this is going to have a positive charge buildup. I want to flip this over so that the negative and positive align, so you can generate your molecule that looks like this. And then here's your negative charge buildup. Again, your electrons from this negative charge will go to the positive, and then you have your cycloaddition occurring. So now the substituents are going to be 1, 2 to each other. So your relationship of the product would be 1, 2. That's going to be formed. This other product will not form. Pericyclic reaction, Diels-Alder reaction is an example of a pericyclic reaction. Woodward and Hofmann predicted reaction products using their theory of conservation of orbital symmetry. Molecular orbitals must overlap constructively to stabilize the transition state. So if we look at molecular orbitals in terms of these Diels-Alder reactions, a symmetry allowed reaction would be of butadiene and ethylene, right? So if you want this to work out, your diene contributes electrons from its highest energy occupied orbital, shown here. This is the HOMO of butadiene, in which you have plus, plus, minus, minus. Here's your node. And it reacts with the dienophile, in this case ethylene. It receives its electron from its lowest energy unoccupied orbital, shown here, the LUMO, in which you have the anti. These two overlap, right? The signs are the same. These are the signs are the same. So that's for symmetry allowed. The forbidden cycloadditions would be in the case of, this is a 2 plus 2 cycloaddition, where you have 2 ethylenes overlap to form the cyclobutene. It has antibonding overlap of HOMO and LUMO, so you have HOMO of one and then LUMO of the other coming together, reacting. You form a bonding reaction here, but this is an antibonding reaction, and this would be a forbidden cycloaddition. So in order for that forbidden cycloaddition to actually work, you can actually add photochemical or light to induce the reaction, so that you take, here's your HOMO, here's your LUMO energy. In the ground state, your ethylene ground state, you just have the 2 electrons being occupied in the HOMO state. However, if you add light, right, you can then induce this so that one of the electrons go into the pi star state. So this is your excited state as a result, which will, after absorbing that energy or that photon, it will allow the cycloaddition to occur, because then the orbitals will line up. So for 2 plus 2 cycloaddition, in order to make them bonding interaction, you can use photochemical or light photons to allow this reaction to occur, but which was naturally forbidden. But through the addition of light, you can now switch, right? So that now it's a bonding interaction, and you can actually perform the reaction. You can look at pi to pi star for ethylene and butadiene. So here's ethylene, here's butadiene. In ethylene, normally the electrons in the ground state are occupied in the HOMO, and then you can have it occupy the LUMO through in addition of energy, but it will require about 686 kilojoules. If we look at butadiene, same thing. All of them are occupied, right? On the ground state are occupied. In order to go from HOMO to LUMO, you need to add light. You need 540 kilojoules to have the excited state of the butadiene. So many of these conjugated diene or conjugated systems have UV absorbance, and so we're going to talk about obtaining a UV spectrum. So here's kind of the nuts and bolts of a UV spectrum, where you have a source with a monochromator, and then you have a reference source with your solvent, and then your sample that is dissolved in the solvent. And so you're going to have an incident reference beam from the reference versus, as well as the sample, which will be generated as the source of light is being passed through. And then there's a detector that can detect what is coming out of the either sample as well as the reference solvent. And then it generates a spectrum, which essentially plots the log of your sample and reference versus the wavelength. So the spectrometer measures the intensity of a reference beam through the solvent only. That was the IR, right? And the intensity of the beam through the sample, which is the I sub S. Absorbance is the log ratio of this solvent over the sample. So in terms of UV spectrum, so it's plotted as a function of wavelength. It usually shows a broad peak. You read what is called the lambda max from the graph, or the peak of the actual spectrum. Absorbance A follows Beer's law. A equals the molar absorptivity times the concentration of the sample and the length of the light path in centimeters. So here's an example of a UV spectrum of isoprene, right? So like I said, conjugated systems exhibit UV absorption. Here's it as a function of the wavelength. Here's your wavelength maximum at 222. Here are some samples of UV absorption: ethylene, cyclohexene, hexadiene. While these are not conjugated, these are isolated double bonds. It exhibits a lambda max. As you get to conjugated system, it shifts it over to a higher wavelengths. So you're going from things that are in the hundreds, now things are in the 200s when they're conjugated. And as you get to more conjugated system, these are conjugated trienes, those number gets greater. So something to note is that a good rule of thumb is that an additional conjugated C double bond C or double bond increases the lambda max about 30 to 40 nanometers. And having an additional alkyl group also increases it about 5 nanometers. Some useful base values that you should know are shown here in terms of conjugated dienes and their lambda maxes. So here's another problem asking you to rank the following dienes in the order of increasing lambda max values. Their actual absorption are 185, 235, 273, and 300. So here are the lambda max values, starting with 185, right? So the one that's lowest is going to be the isolated diene shown here. This is then followed by, these are all conjugated dienes henceforth. However, this is not in a cyclic system. In a cyclic system, the lambda max values increase. So as a result, this would be followed after 185, so the 232. Actually, it should be 235. Excuse me, that's incorrect. And then between these two, this has 3 conjugated double bonds. This has 2. As a result, this will be in the higher wavelength versus this one. And so this is how you would order it. If you're going to compare to the actual values, here's a description describing the actual values. So looking at it and saying, oh, this looks like, for example, this looks like 3-methylene cyclohexene has 232, but then you'll add 5 nanometers because you're adding these methyl groups or these alkyl groups. This one looks like cyclohexene 1,3-diene. It has a substituent that's a donating group. As a result, it increases the value from what it is. Here, this one looks like cyclohexane-1,3-diene again, but this one has, in addition to the methyl group, it has donating group, methylene. It has an extra conjugated system, which increases the value. And so this ends Chapter 15, Part 2.